Next, I'll be discussing an approach that we developed for automated curriculum learning in our lab called task facing. And in this, we actually generate a curriculum using with the help of demonstrations, where the easy or simple task would be to imitate the demonstration, doing imitation learning, and the difficult, more complex task would be to learn the optimal policy for my target reward and surpass the performance of this suboptimal demonstrator that I'm learning from. And to do this, we propose two approaches: temporal phasing and reward phasing. Temporal phasing changes the transitions in the MDP by sampling, varying the sampling between the expert policy, which is the demonstrator policy, and your RL policy. In reward phasing, we, instead of assuming a policy, we use the demonstrations to learn reward function using inverse reinforcement learning.
Oh, we saw that, right? Yeah, we saw that in imitation learning.
Yes. And using inverse reinforcement learning, we learn a reward which will help the agent mimic the demonstrator again, and then gradually we phase out that reward to focus the agent on the true objective. And we see that the manner in which temporal phasing and reward phasing creates the curriculum leads to the generation of a task continuum.
So I'll just remind our viewers that so in inverse reinforcement learning, we saw this previously in imitation learning. We saw the IRL approach, and we saw that it produces a policy that is as close as possible, under some approximation limitations, to the demonstrator policy, with some conditions on the fitted reward function. However, we can use the same approach and not output the policy, but instead output the reward function. Right? So in inverse reinforcement learning, if you remember, we learned the reward function, that if that reward function is optimized using reinforcement learning, then the policy, or that's the hopes, that it's as close as possible to our demonstrator policy. So here, Bajaj et al. Did the same, but only took the reward function from the IRL process.
We also show in our paper that the task continuum that we generate using our approach, that assuming that if the optimal policies for each task in this continuum are continuous, if we assume that the optimal policy for each task in the continuum leads to a continuous function, the policy space, and if we make sufficiently small transitions along this continuum, that means we change the task ever so slightly along the continuum, we can guarantee the trust region approaches, which we studied about, they provide guarantees of monotonic improvement within a trust region update. So our guarantees show that for by moving along this continuum gradually, if the optimal policies for all the tasks are continuous, the KL divergence between the optimal policies of any two of consecutive tasks in the curriculum can be bound by any arbitrary value. And due to this, trust region approaches can be used to learn the policy along this policy continuum while showing monotonic improvement towards our target policy. So this is achieved by leveraging the smoothness of the policy landscape and using the trust region guarantees to progressively guide the agent through the task sequence. We conduct experiments against baselines such as HER with demonstrations also added in its sample space and to its loss function, IL, adding an imitation-based loss function to it. We also compare against adaptive imitation learning approaches, and we show that our approach does better than the demonstrator in all three domains. So our approach is the reward phasing is the green line and temporal phasing is the blue line. You see that temporal phasing worked very well in the pi flags domain, which is a game of capture the flag between two tanks. We'll see that momentarily. And in the fetch domains, which are goal-based domains, which we showed earlier, HER is known to work very well here. But we show that although we don't get maybe the same sample efficiency, we do learn the optimal
asymptotic performance.
we do outperform it in asymptotic performance. You can't say we learn the optimal, but we do outperform HER in asymptotic performance.
Yeah, let me again just
phasing.
Remind the readers in RL, we call sample efficiency represents the learning speed. How quickly are you able to reach the asymptotic performance? And you can see here, for instance, the orange line is very sample efficient. It reaches the asymptotic performance very quickly. However, when we discuss asymptotic performance, it's the post-training performance. We can see that with respect to asymptotic performance, the green curve is better. Green curve is reward phasing is better than the orange one, which is AGR, the handset experience.
Of course, there are various other evaluation metrics for our curriculum, and we will go over those momentarily. Here we have an example, it's a short demo showing how the reward phasing approach learned to outperform the demonstrator and learn to perform the task in the pi flag, capture the flag domain. And so here the red agents are the opponents and the blue tanks are the RL agents. It's just one RL agent, the blue tank, versus one predefined controller used for the red agent. We use the opponent as the demonstrator initially, trying to learn to mimic the opponent, which is our demonstrator. Eventually learn to behave the demonstrator, performing about the same, getting about the same score for both red and blue. Eventually, as we start the phasing process along the continuum, we see that the policy learns to outperform the demonstrator, which is our opponent in this case, and achieves a higher score. And then finally, we learn a policy which achieves the maximum asymptotic performance compared to the baseline.
So by the way, this is an interesting domain because here, I guess intuitively, we can ask our viewers maybe to suggest curriculums here. Intuitively for this game, I think everyone can think of reasonable curriculums, right? For instance, learn how to shoot the opponent, learn how to avoid being shot, learn how to take the flag, learn how to bring the flag back, stuff like that. And then eventually combine all of them to a single powerful player that learned all of these sub-modules, sub-tasks. However, that might work well, but that's a bit a step away from general AI, right? In general AI, we would like to automate everything, to have everything decomposed, broken down automatically, algorithmically, instead of needing to rely on an expert. And so the reward phasing approach does not assume any knowledge of the domain, right? I mean, it works. It could work on other domains as you showed.
Yes, it's
domain
independent. Yes.
Domain independent, right.
Finally, we'll go over some popular evaluation metrics used in curriculum learning. Although curriculum learning does differ from transfer learning in some regards, it does extend transfer learning to multiple tasks. So we find that the same metrics used to evaluate transfer learning can be used to evaluate curriculum learning. Two metrics that we already just discussed were learning speed, which is our sample efficiency, which measures the time or number of iterations required for the agent to achieve a specified threshold level of performance. Another way we can compare them is just final performance, which could be the asymptotic performance or success rate or task completion time. We also have a transfer efficiency metric, which assesses the benefits of the curriculum in transferring knowledge from source task to the target task compared to training from scratch. So if I can learn to perform the target task by just without the need for the curriculum, by just using vanilla RL, then the point of the curriculum becomes it becomes moot. It's not efficient for me to use a curriculum, so its transfer efficiency would be very low. And this is commonly known as negative transfer in transfer learning and curriculum learning. So you want, for efficient transfer, you'd want the curriculum to lead you to learn the target task more efficiently than without the curriculum. We also have metrics on robustness and generalization, which tests the agent's performance across diverse and unseen environments, sees how well the trained agent can generalize. Stability is more about how the curriculum is designed so that every time we do train on it, we get less varying performance. We get consistent performance. So
consistent performance with respect to the target test?
Yes. So this is if I train taking 10 initial policies on the same curriculum, how likely am I to still learn to get a good performance on my target task? So if all the policies can do a good job, if the curriculum does a good job of training all these policies, we can call it a stable, high stability curriculum. Whereas if a lot of them fail, we wouldn't call it a stable curriculum. And finally, we have curriculum efficiency, which evaluates the computational cost or resource usage of curriculum generation. Training on additional tasks might help the agent, but it's computationally more expensive because now we have to train on multiple tasks. Of course, training from scratch might lead you to never learn, but it's still important to generate curriculum which are efficient compared to other curriculum which might be inefficient.
Right, on the other hand, right, if you have a simple task, I don't know, lunar lander, and we break it, I mean, there's no need to do a curriculum there. It will just hamper or make learning slower.
Exactly, that'll have low transfer efficiency.
Right, yeah. So you want to balance the actual need for a curriculum in each domain.
Yes.